Welcome to This Explainer. Today, we're taking on a topic that, let's be honest, probably causes way more anxiety than it actually should: understanding statistics in quantitative research. Whether you're out there conducting your own studies or you're just trying to get through a research paper without completely losing your mind, statistics are literally the essential tools we use to make sense of numerical data. All right, let's just address the elephant in the room right off the bat. It is completely normal to feel a bit overwhelmed when you first run into a giant wall of data, those complex formulas, and all those Greek symbols. On the surface, yeah, quantitative research can definitely look like it's written in some secret foreign language specifically designed to keep people out. But here's the reassuring truth. Once you get the hang of the vocabulary, the logic underneath it all is actually incredibly intuitive. When you strip away all the complicated equations, statistics is really just a structured way of doing two basic things: summarizing numbers clearly, and then figuring out if a pattern you're seeing is actually real or just a random fluke. That's the whole shebang. It's just a mathematical way of asking, hey, is this pattern just due to chance? We've got a really clear roadmap for this explainer today: demystifying statistical data, core foundation concepts, the logic of hypotheses, choosing your statistical test, statistical versus practical significance, and finally, putting it into practice. Starting right off with Section 1, Demystifying Statistical Data. So when we look at data, there's a pretty stark contrast in what we can actually do with it. Descriptive statistics, they just tell us what the immediate data shows. Think averages or frequency counts. It describes exactly what is right in front of us without trying to generalize. Inferential statistics, on the other hand, take a leap. They use data from a small sample to draw conclusions and estimate what's happening out there in the broader world. And because it's a leap, well, it always comes with a recognized margin of uncertainty. Moving right along to Section 2, Core Foundation Concepts. Now, the big takeaway here is that researchers almost never study an entire population. I mean, imagine trying to test every single English learner in an entire country. Because populations are massive, and their exact characteristics, which we call parameters, are unknown, they're represented mathematically by Greek letters like mu. So instead of the whole population, we rely on a sample, a manageable subset. Characteristics calculated from a sample are called statistics, and for those we use standard Roman letters like m for mean. We're essentially using that sample statistic to estimate the unknown population parameter. And this brings us to the famous normal distribution. You know, that symmetric bell-shaped curve you've probably seen 100 times? It is absolutely foundational to quantitative research. Most scores cluster right there in the middle, with progressively fewer scores out on the high and low extremes. This specific shape is a really key assumption for a lot of the statistical procedures we rely on to make those leaps from our sample back to the population.
Next up, Section 3, the logic of hypotheses.
I always like to think of the null hypothesis as sort of like a dragon that the researcher has to slay. It's basically the default, kind of boring assumption that absolutely nothing interesting is happening. It assumes there's no effect, no relationship, no difference whatsoever in the broader population. And this stands in direct contrast to the alternative hypothesis, which is, of course, what the researcher is actually hoping to prove, that an effect or difference really does exist. So how do we slay that dragon? Well, in the social sciences, researchers conventionally use a significance level, or alpha, of 0.05. What does that actually mean? It means researchers are willing to accept a 5% risk of wrongly rejecting a true null hypothesis. For better or worse, it's become the widely accepted gold standard of proof. Which leads us directly to the p-value. Basically, the p-value tells you the probability of getting your observed results if that boring null hypothesis were actually true. If your calculated p-value drops below that magic 0.05 threshold, bingo! You reject the null hypothesis in favor of your alternative. But researchers really have to be careful here. You can make a type 1 error, which is a false positive, saying an effect is there when it's not. It's like a fire alarm going off when there's no fire. Or you can make a type 2 error, a false negative, which means you missed a real effect completely.
That takes us to Section 4, choosing your statistical test.
You see, you absolutely have to match your statistical test to the specific type of data you're working with. Parametric tests are like the heavy hitters. They are super powerful, but they're incredibly picky. They assume your data is roughly normally distributed and measured in very specific ways. Non-parametric tests, on the other hand, are your flexible alternatives. They make way fewer assumptions about the shape of your data, which is great for simpler categories. But the catch is, they trade away a bit of that statistical power for that flexibility. This breakdown is honestly a perfect little reference guide for the most common inferential tests you're going to encounter. Notice how a t-test is specifically used for comparing the averages of just two groups. If you add a third group to the mix, you have to upgrade to an ANOVA. A correlation, that looks at the relationship between two continuous variables, like, say, motivation and test scores. And a chi-square looks for associations between categorical variables, like gender and preferred learning strategies. Ultimately, the test you use is directly dictated by your research question and your variables.
All right, rolling into Section 5, statistical versus practical significance.
This idea really hits the nail on the head. You see, a massive sample size can actually make a microscopic, basically trivial difference look statistically significant. If you test 10,000 people, even a tiny 1-point difference on a test might flag as a p-value under 0.05. And that is exactly why researchers must also look at effect size, which is a standardized measure of how large a difference actually is. It measures practical, real-world meaning, not just mathematical anomalies. So when you're reading a research paper, you're almost guaranteed to run into a jargon-heavy string of numbers, just like this. Let's deconstruct it piece by piece, okay? The T right at the start tells us they used a t-test. The 58 is the degrees of freedom, which is tied to the sample size. 2.85 is the calculated value from the test itself. The P equals 0.006 tells us it's statistically significant because it's well below that 0.05 mark. And crucially, the D, which stands for Cohen's D, is 0.73. That proves the difference isn't just mathematically there, it actually has a medium to large, practically meaningful effect size.
Finally, Section 6, putting it into practice.
Let's imagine a quick scenario. Say we have 30 learners in a task-based instruction group, and they score an average of 78 on a post-test. Meanwhile, 30 learners in a traditional instruction group scores 71, so we've got a 7-point difference. But as researchers, we need to know, is this 7-point difference a real reflection of the teaching methods, or just chance variation in this one specific group of students? So here's your exact step-by-step checklist to figure this out. First up, we're comparing the means of exactly two independent groups, right? Because of that, we check our assumptions, set our alpha at 0.05, and select an independent samples t-test. We run the numbers, check if our resulting p-value drops below 0.05 to see if it's statistically significant, and finally, we calculate that effect size to ensure the 7-point difference actually matters enough to change how we teach in the real-world classroom.
Now, before we completely wrap things up, it is absolutely crucial to watch out for some common pitfalls. One of the biggest traps out there is treating a non-significant result as absolute proof that no effect exists. Actually, sometimes a study simply lacked the statistical power or the sample size to detect a real effect. Also, definitely beware of papers reporting p-values without effect sizes, or researchers who run dozens of tests and then only report the ones that magically hit significance. Always decide your analysis plan in advance.
Armed with this structured understanding of everything from populations and p-values to effect sizes and test selection, you're no longer at the mercy of intimidating equations or a massive wall of Greek letters. You're now equipped to look past all those dense formulas and actually critically evaluate the evidence being presented. So the very next time you open up a quantitative study, ask yourself, did they actually slay the null hypothesis fairly, and does the effect even matter? Thanks so much for joining me on this explainer, and keep asking great questions.